Is that from your link that you put up?
Yeah.
Where on Facebook?
It's also, if you go to my Instagram, it's my little link bio.
That makes it easier.
No, you're
I don't have good service.
Yeah, they have the school internet.
Yeah, you should be able to get onto the UCI Wi-Fi. You can see it. Can you hear me?
Oh, yeah, there you go.
Very
Very good.
Okay, now I want to test something else. On the live stream,
I can't hear you.
There's 20-second delay.
but you can still hear me talk because I muted it.
I can't hear her.
No, I can.
Do I need
Yes.
to mute her or something?
Yeah, it might be.
All right, go. I can't hear you in school. I don't know.
Is that your YouTube channel?
Can you still see me now? Is it too dark?
It's a little
It's a
dark.
little dark.
It has lights above it.
You see what you see on your computer.
Oh, so it's. I have to brighten it.
Oh.
Let's see.
Oh, okay.
I can try to make it brighter.
Yeah.
Like that.
Okay, that's a lot better. I can see myself a lot better now.
But can you see him better?
Yeah.
Is it better?
So it's understood.
Yeah,
It's fine. It's fine.
If you brighten up too much, then the pictures get washed
Oh,
out.
there it is.
There you go. Yeah, that looks a lot better
Yeah, am I looking dead on a
now.
Hold on.
Daddy wanted a piece. Hold on, look, there's a tiny piece right here. You're not gonna share with Daddy?
You should sit over here.
A tiny piece right here, baby.
She wanted us on this side so that way she wouldn't.
Oh, she's not staring at us.
Yeah, because usually when I'm standing here, I make a lot of eye contact with this people, so that way I won't.
So we'll just see your back.
Yeah, that's them down there.
No, I'm gonna stand right here.
Oh, right there.
I don't ever go up there.
Oh,
People will sit here.
Okay, you need to face towards them more.
Yeah. So just sit in that vicinity.
That's a focus right here.
this is only water.
Everybody's texting me. It's like I got married or something.
Oh, I'm sure that'll be exciting too.
Nah. Nah.
Yeah, wait till you do.
Wash down that cake.
Here.
Hi, Eric.
Hi.
It's my family.
Hi, family.
You've met my mom before.
I did.
Inhaler.
Oh.
Holly.
Alright.
This is my aunt, Kristen, my advisor, Eric. And then I think you met Ashley. That's Madeline
Hi, Madeline.
and Ashley.
Hi, Ashley.
And then her husband, Marcel.
Hello.
Madeline.
Thank you for introducing
Thank
me.
you.
Oh, my pleasure. Thank you.
Madeline, Mindy doesn't need to do this.
Maybe there's next
But she
one.
likes it.
Our next one?
Yeah.
Okay, sign her up.
Okay, run.
All right. Need anything?
No.
Right. Yeah.
Maybe $1 million.
Okay.
What?
Everybody hates to say this.
Who hates us?
The baby's here.
Did he you?
What's that? Or somebody's little bracelet.
I'm gonna, yes.
Go, Daddy's gonna get you. Run out here. Run out here. Run out here.
How many people are there?
It could be full.
Right.
Fighting. You still online?
Yeah, so anybody that comes in now, they're gonna see me dancing and running around. But it's not public. Only people with the. Oh, I'll save you. I'll save you. I got you. You're safe. You're safe.
Give me.
No.
Mindy is busy.
She needs to start calling down. That's 15 before.
10 minutes. I want to start burning off.
I don't have to do that.
Find the fit.
Have you to the
Run out here. Run out here. Run this one.
Hey, Kaden.
You're giving away the whole show already.
Giving it away.
Jeez.
I'm running.
I've been running around playing catch me. So
He's sweating for this thing.
Okay.
Get you there.
Go this way. Go.
I'm trying. It's so hard.
because I've always seen everyone else doing it. So now
I put on my rounds up and down steps. 'Cause I'm
No, they can be in.
15 more minutes to penny if they're in suicide or.
I just gotta burn off some.
we're a very inclusive family oriented department.
It's exciting, man.
What happened?
You wanna give me a hug? You wanna give her a hug?
No.
You're my parent.
Hey. Hi. Good. Thank you. I've been playing catch me, so I'm
Alright, now she probably won't be mom, but Pauline's my first name.
Hi, Ashley.
Suggested, along with our daughter. Marcel.
I'm in Chris.
That's my aunt, Matt's dad, and mom.
Thank you for letting us stay.
Yes.
That was super helpful. I haven't been able to figure out showering in two places. Sure, I'll figure it out. Come out, shower now.
It was.
Yeah, it has two faucets. Yeah. I'm excited.
Weather times, guys, for you.
Yes.
You guys see my phone?
Oh, Charlotte told, I think they're gonna walk over this evening and walk over.
Oh,
Yeah.
She's incredible. French baker.
I'm excited. Whenever she bakes stuff, y'all hide it from each other.
They'll be gone once it starts. The girls will know.
Where do you?
I'm gonna talk over there. Yes, this is a very interesting shaped room. It's meant to be the UN, right? So no one's at the front of the table or the head of the table.
Okay.
But you guys can sit over here.
Security.
Yeah.
Again,
Where do you want us to sit?
It's probably
Maybe
the
in
ones
this
at the center of the
Okay, like here?
Yeah. Or in the back, whichever.
I think we better go to that for a while. Yeah, no, worries.
Cheers.
Oh,
Yeah.
if not,
People
can
stand.
She said people will stand.
People trickle in like right at it. BSS is known for being
I was gonna
perpetually.
Yeah. You guys.
This, 10 days.
10 days power.
Well, look, he's early.
Well, he's in my lab, so.
Oh.
This is Caden. He's an undergrad that's working in our lab. He's actually gonna go to grad school up at Oregon State.
Oh, wow.
Yeah, doing ice core stuff too.
Yep.
Awesome.
Yeah.
Have you been to the outing yet, or?
No, want to though. We'll get there one day. I think,
Well, if he's ice core study, he might get picked.
I think we do have a trip planned for probably 3 or 4 years.
With the Greenland project?
I'm not sure, because I think we might try to just get like a quick fern garden in Antarctica. But if we can hitch on the Greenland project, that would be good.
The soundboards, whatever, the patients.
Yeah, the iPad's pretty good in this building.
I need to take out my teeth. Here comes my crew.
Good. So maybe is this exciting piece sitting for people?
Probably these seats here. I mean, honestly, the committee sits wherever they want usually. I'm not pointing to any seat.
Wow.
That's how to get around it.
Yeah.
It's not until you go to the.
I'm doing good. Oh, yeah. Well, I've been playing catch me with my niece, so she's about to be 3.
Isn't that a great age?
And she repeats what you say. She can remember.
I know, it really is true. I have a 3-year-old.
Yeah, she's
Oh my
got-
word,
And they-
they're sprawling, yes.
She's so smart. I hope she's quiet, but if not, don't walk
It
around.
doesn't matter.
And
It
maybe
just
that's
doesn't
still on.
matter. It'll be good exposure, you
Yeah.
know?
Plus, we are an inclusive department.
That
Family
absolutely is right. It is absolutely, I just remember Pelosi swearing in the new
With the
Congress.
kids.
It was a brilliant idea.
Yeah, it's the next generation of people, you know?
I'll be back in a minute.
Okay.
Yes, yes. For our family.
Are they looking right now?
Yeah, a couple of them, yeah.
I can't even see, so we're just gonna wave. Hi.
Hey, everybody. Yes, we made it.
Hello. It's my YouTube live.
Your YouTube live?
We
Yeah.
have family everywhere, so it's.
That was really smart.
Yeah.
Thanks for coming.
Yes.
No. Right. Oh, yeah. Whatever you. You have a good one. I just don't think it's right.
Yeah.
She said she saw me.
Bounded by 2 Zacks.
Yes.
Zach sandwich.
It's too late.
We haven't, yeah.
Hey, you guys are all staring at me. It's like. But when I practiced, no one was in this room.
It was spring. I did not.
Oh, no.
We can go up one down if you want. Up one down the inner ring.
I'm still good, I'm still at 90.
You get like 2 days.
Well, I was Friday morning, and then today it's just busy. Friday, and today it's like, we were like this. I walked out too.
Well, that's an hour to work.
No,
And comes down an hour and a half, just like any computer. And, my work here stays with that, and they leave that, so, can't work. I'm gonna try to quickly fill in the second hand sheet for the duplicate during that time.
That's pretty good. Yeah, it still frees up, still productive time.
Yes, I did know, so, yes. The windows don't have.
call him real quick, just make sure.
7. Okay. 8, 9. 11.
Well, you have to pass it up on the pastel?
Not 10. I was thinking of the.
Oh, okay, yeah.
My reputation.
High reputation. Everybody's seen that one. Yeah, well, I will be here.
Yeah.
Fancy meeting you here.
Hey, no collusion.
I know.
No collusion.
We are.
Sure. All right. You know what the protocol was.
Yeah. We haven't seen it yet, so it'll be a week.
Yeah. This way we can keep each other from missing.
That might be.
I don't like that, so I'm gonna discuss it.
Sweet.
Yeah. One was like.
Good, because I know your phone goes to the freezer.
That
was good.
Sterile.
I was there. But and it's interesting because Jefferson Village.
Yeah.
Just because like he's for sure.
He couldn't just roll his chair. Well, he was supposed to sit down. He would roll his chair.
I saw both
Sweet and with 3 goals.
Got
We were together.
I guess I'll fill out this space.
Yeah, so this is actually a live stream, so everyone can see me right now.
Oh, really? Who's seeing me?
It's on YouTube, but it's like, I sent it to my family so that they could watch the ones I couldn't make
Oh,
it.
that's good. Hello, family.
Yeah.
Where is it? I should watch it on my phone.
Oh. I'll send you the link so you can rewatch it later when you want to.
Oh, it's gonna be forever
Rethink
there.
it.
I guess you also upload it.
Well, it's private, so only people with the link can access it. Yeah.
I see.
Like graduates.
Yeah. So.
Sounds better.
No. They had snuff. Some Swedish. And so lunch. Shaking. So.
Chair. You might have a seat up there. Oh, no, sure.
I should know, talk to her.
They're not here.
I'm missing two of them.
He was.
Got it. Okay, so he was.
Because he's doing. It wasn't like that. I don't feel good. It's good to be here. It's good.
Yo, buddy. This is YouTube live, so
I'll try not to knock it off.
Yeah. Yeah.
We need a spot for it.
there's like so many people here. We have more chairs. I mean,
Okay. I'm not so Yeah.
Yeah, Mike.
I'm also
Supposed to be here. 1 minute to go.
I'll figure it out.
Yes.
he was in here earlier and he said hi.
Okay.
Yeah, that's my mom.
Okay. I mean, no. But if not, then it's not.
Yeah, we need it. There he is.
She has to find Yeah. Yeah. I mean,
Okay.
what is it?
We need to find you a seat.
I don't know how to say it. Okay, sure. Yeah. Yeah, just try to like focus mostly on.
All right, very good. So let's get started. Thank you all for coming. We're here for the PhD defense of Mindy Nicewonger. So before we start, I'll just tell you about the process a little bit. So Mindy's going to talk for about 40 minutes to describe at least some of what she did for her PhD research. After that, there'll be questions from the audience, after which we'll let you all go and Mindy will meet with the committee. And the committee consists of Ellen Ruffel, Don Blake, and Michael Prater. Okay, very good. And I'm Eric Saltzman. Okay, before we start, I'd just like to mention a few things about Mindy. You may all feel like you've known Mindy forever, and that's because Mindy has been affiliated with us for quite a while. She was here as an REU student while she was an undergraduate from Texas A&M, where she got her PhD and her bachelor's degree in meteorology. So she came to us in 2013. And let's see. So Mindy has won quite a number of awards. I'm just going to mention a couple of them here. She got an NSF Graduate Research Fellowship, which is an impressive and highly competitive thing. She got a UCI Chancellor's Club Fellowship last year, and she was awarded the Most Promising Future Faculty Award, which I think is something few of us could claim on our record. So very, very impressive. And I would just note that her awards come from both her scholarship and also her contributions to outreach and education, which is quite impressive. Anyway.
Thank you. Okay, thank you all for being here today. I did not expect this many people, so thank you for giving me your time. So the title of my dissertation research is Ice Core Records of Ethane and Acetylene for Use as Biomass Burning Proxies. So first, what is biomass burning? Because my mom is in the room. It is the natural wildfires on Earth. So I'm trying to understand how they have changed through time by using ice cores and gases inside of them as my tool. So why is biomass burning important? Okay, so I might use the term fire interchangeably, just to keep us on the same page here. Fires release a lot of gases and particles to our atmosphere, and that alters the atmospheric chemistry and composition. And in particular, fires release a lot of methane. And so as we move forward with climate change, understanding how much methane could be in the atmosphere is quite important. Fires also alter our surface albedo, or the reflectivity of the surface. So over long time periods, if you have large changes to the fire system, you can change the radiative balance on Earth. And from 1997 to 2016, fires released about 2.2 petagrams of carbon per year, which to compare is about 25% of the fossil fuel carbon released either during that time. So fires are an important part of our climate system, and understanding their variability through time is really important. So biomass burning is an important source of methane, as I mentioned. And here I'm showing you the ice core record of methane from the Epicodome C ice core, which spans the last 800,000 years. So on the horizontal axis, you'll see the time scale with 800,000 years ago on the left and modern or 1950 at 0 on the right. And you can see that over the course of the record, methane levels span from about 300 to 800 parts per billion. That means for every billion molecules of air, there's about 300 to 800 molecules of methane. We see the big ups and downs in this cycle, and we know that that's going from our warm periods, our interglacial periods, into our cooler glacial periods. But there's a lot of variability superimposed on that record, and the question that still really lingers in the scientific community is how much of the methane variability was due to fire. Okay, so in the pre-industrial world, when we no longer have this huge fossil fuel source of methane, that fire component becomes more important. And so what we really need is to understand past fire emissions in order to validate our fire models and to also better understand what's going to happen with methane. So the next question would be, well, how did biomass burning or fire vary in the past? Well, that's a really good question, and I don't think we know an answer yet. So here I'm showing you a compilation of 3 different biomass burning proxies. So the time scale here is just the last 2,000 years in the unit of calendar year. So 2,000 years ago is on the left and modern is on the right. The vertical axis is just more fire up, less fire down. And there's 3 records here. So we have charcoal, which is in black, methane in blue, and carbon monoxide in red. Okay, so first charcoal. Charcoal is a qualitative and regional record of fire activity. So basically what happens is a fire happens somewhere and it leaves behind charcoal in the sediment. And many years later, really awesome scientists can go out and measure fire activity in different regions. And you can do some statistics and modeling to get a sense of global fire activity from charcoal. And the reason I'm emphasizing activity is because it doesn't tell you anything about how much material was burned and therefore how much emissions you get into the atmosphere. Okay, so you can see some pretty large variability in that black line. And then we have methane and carbon monoxide. Both of these records are from ice cores, and it also requires the measurements of their stable isotopes. Okay, so stable isotopes are like the fingerprint of a certain source of these gases. And so you need that fingerprint in order to deduce how much of their budget was from fire. So if we look at these records, and also these records can tell us about fire emissions, because we can go backwards from the amount of methane or carbon monoxide and infer how much material was burned. So if we look at this record, we see that there's some pretty obvious variability. Right around 1500, which is denoted with that blue area called the Little Ice Age, or LIA, we see that all three records kind of reach a minimum at that point. So that's something they share in common. But if we move forward in time, say around 1850 or so, we see that the carbon monoxide and methane records both increase, and the methane record stays low. Okay, so at that point, we see a huge divergence in what these different proxies are telling us about fire. And then what's really important here is what they're telling us about modern fire. So if you follow the black line and the red line, they both go down to a minimum, to a low level, but the methane line goes up, meaning fire emissions today are the greatest they've been in 2,000 years. So a lot of fire models actually use charcoal as their validation tool. So I'm already telling you right now that that's probably not a good idea. All right, so we still don't really know how biomass burning is varying in the past. So the motivation for this thesis is, can non-methane hydrocarbons, or these trace gases, be measured in ice cores and be used as biomass burning emissions proxy records? I want to look at different gases that can tell us about fire emissions. So there's three goals of this thesis. The first was to develop an analytical method to measure these gases, because no one had measured them before. And then second, analyze some Greenland and Antarctic ice cores, and in small parentheses, go get ice. I want to highlight all of that work I did because it's important. Okay, and then three, explore the implications of ice core records of acetylene and ethane for the pre-industrial biomass burning emissions. All right, so why ethane and acetylene? There's thousands of different gases in our atmosphere, but why these two? Well, these gases are short-lived, and that means that their atmospheric lifetime is shorter than the time it takes for air to mix from the northern hemisphere into the southern hemisphere, and that time scale is about a year. So the mean annual lifetime of ethane is about 2 months, and the mean annual lifetime of acetylene is about 2 to 3 weeks. So in a sense, these gases live and die in the hemisphere in which they were emitted. And so if you have a record of these gases, say from Greenland ice, you can infer the emissions in that hemisphere alone. So we get a Greenland and Antarctic record, it can tell us about global fire or global emissions. They also have simple atmospheric budgets, and this is important because it makes it hard to interpret certain emissions if there's 10 different sources. So here I'm showing you the modern atmospheric budget for these gases. Both ethane and acetylene are released from biomass burning and also from biofuel burning, which is the use of fire for human purposes, such as cooking in their homes. Then we also have fossil fuel sources, and then also ethane has a geologic source, and geologic emissions are the natural outgassing of the earth. But there's an asterisk next to this source because that source through time is not well constrained. And also, if it even exists, is something else that we're trying to figure out. So there's an uncertainty on that source. Acetylene may have a source of geologic emissions. Again, it's not been well quantified before, so I'll talk about what that could mean near the end. Both gases are removed in the atmosphere via reaction with the hydroxyl radical. And then ethane also has an additional loss term to chlorine included in a lot of the budget analyses of ethane, So I'm going to also incorporate that into my interpretations. But if we go into the pre-industrial atmosphere and we get rid of the fossil fuel term and greatly reduce the biofuel term because population gets real low, then we can understand the variability in biomass burning and geologic emissions from these two records, because ethane will have two sources, biomass burning or geologics, and acetylene really only has one, which is biomass burning. All right, so pause. So I really want to highlight the fact that I did a lot of field work. So sometimes that gets lost to the ways, but I spent 7 months of my PhD doing field work, and a lot of the work that I did ended up in my thesis. So I just wanted to highlight what goes on in ice core drilling. So I went to the South Pole to help drill the South Pole ice core, which I subsequently. So here I'm showing you the drilling process. So we're outside, temperatures are probably about minus 20 degrees Celsius. And you can see the barrel is coming up out of the borehole right now. And every time we go into the borehole, we were able to pull up about 2 meters of ice. This ice core ended up going to 1,751 meters depth, which spans about the last 54,000 years. But my research is really focused on just the last 2,000 years. But my job down in Antarctica was to be an ice core logger. So my goal was to make sure the ice got back to the US all in one piece, well, 1 meter pieces. And we knew the depth well on those ice core samples. Because an ice core sample without a depth is meaningless because we don't know how old the ice is. So all that ice finally makes its way back to the National Science Foundation's ice core facility, which is outside of Denver, Colorado. So many weeks in the summer, for many years, I was in those freezers, or big walk-in freezers, collecting ice core samples that then I shipped back to the lab here at UCI. That's a box that I opened up, box number 6 there, very well packaged. I'm a really good ice core packager. And then in 7, there's me actually analyzing one sample. So when you see the next plot, I just want you to emphasize how much work goes into getting one sample. All right, so how do I get the air out of the ice cores? Well, I use a wet extraction or a melt technique, which is pretty self-explanatory. I'm melting the ice core sample under vacuum. So here in this schematic diagram on the far right, there's a glass extraction chamber. And in that chamber, I put my 350 gram ice core sample that's been cleaned and prepped. And then I can isolate that chamber after a vacuum has been pulled on it, meaning I remove all of the modern air in that chamber. And then I can slowly melt the ice core sample. It looks something like this. It's pretty visually stimulating. Each ice core sample takes about 35 to 45 minutes to fully melt, and I just watch it melt. But the air is being liberated from the ice, and the gases we're looking at are rather insoluble, and so it comes out of the water into the headspace, and then I can pull that air out using a cryogenic technique, which I'm not going to get into, and then we analyze it for the abundance of ethane and acetylene using gas chromatography and mass spectrometry. All right, so here we go. This is the ice core records of ethane. So on the x-axis is time, going from left to right in the units of calendar year. So again, 2,000 years is on the left and modern is on the right. The vertical axis is the ethane mixing ratio, now in units of parts per trillion. So for every trillion molecules of air, there are between 0 and 800 molecules of ethane. So if we look at this record of Greenland, there's actually 2 ice core sites here denoted with the different colors. You can see that ethane kind of ranged from about 400 upwards of 700 parts per trillion during this time period. What you also notice is there's not really any trend there. Maybe there's some if you really wanted to get into it. But what we see is the mean is about 500 parts per trillion. And over Greenland today, ethane levels are about 1,300 parts per trillion. So we see this huge jump in the amount of ethane, which makes sense because of the fossil fuel source over the Northern Hemisphere today. Okay, so now if we head down south to Antarctica, the modern level over Antarctica today is about 210 parts per trillion. And you can see that all 3 records from Antarctica are less than the modern day level, which again is what we want to see in a pre-industrial ice core record. So for reference, the green squares are the South Pole ice core measurements that were from the ice core I showed you being drilled. But for the first 1,500 years of the Antarctic records, you can see that ethane levels are about 110 parts per trillion. And then if you have a really good eye, you can see that about 1,500 CE, those levels begin to decline. And we don't really see necessarily the same obvious decline in the Greenland data. And so I'll get back to what this could mean in a few slides. Now, the ice core records of acetylene. So again, the same color scheme for the different ice cores. Now the vertical axis is in units of parts per trillion again, but ranging from 0 to 130 parts per trillion. So acetylene is much less abundant than ethane in the pre-industrial atmosphere and in the modern atmosphere. But in this record, we actually do see quite a bit of variability going on. We see that at around 1,000 CE, there's this bump in the Greenland level of acetylene. And then it kind of declines a little bit during the 1500 time period. And then immediately after that, it starts to rise really quickly. And that's probably the early onset of anthropogenic emissions of acetylene. And today over Greenland, acetylene levels are about 160 parts per trillion. So again, the mean level over the ice core record is about 85 parts per trillion. So we see this big change from pre-industrial to modern due to fossil fuel and anthropogenic emissions. Now, if we go down to Antarctica, something different happens. So the first thing to note is the modern level, which is 18 parts per trillion, and that's the dashed line. So you'll see that for the first 1,500 years of the record, Antarctic acetylene levels are higher than the modern day level. So how do you get a gas to be higher in the pre-industrial atmosphere without the addition of fossil fuel or human sources? Okay, so this is something that is very puzzling, but I'll get back to what it can mean in a second. But if you look closely again, you'll see that there's this really large decline in Antarctic acetylene levels during that 1500 time period, which coincides with the same decline we see in ethane. Okay, so if I zoom in on just the Antarctic ice core records with ethane on top and acetylene on bottom, we can see that decline easily. So the decline in ethane is about 35 parts per trillion, or about a 30% decline. And then in acetylene, it's about a 15 part per trillion decline, or a 50% decline. So very large changes are occurring in these gases. And so if you remember from the beginning of this, when I talked about their budgets, the only shared source that is thought to vary on short time periods is that fire source. And so the question now is, well, what were fire emissions doing in the past in order to get these two different ice core records? Okay, so some methods here. So in order to infer emissions of these trace gases, we have to use a model. And so I use Michael Prather's chemistry transport model, which simulates atmospheric chemistry, transport, and loss of gases. And the reason I have to use this model and not just a simple box model is because these gases are short-lived. And so the location of where their emissions are occurring, especially in regards to Antarctica and Greenland, really will impact how much of the gas we get over those locations, right? Because of their lifetime. So what I do with this model is I add some emissions of the gases in a particular geographic location. And so in this panel here, I'm showing you the Global Fire Emissions Database, version 3, global fire emissions of ethane. And the scale is kind of funny. It's a natural log, but it was just to show the colors better. So the greener the color is where we have more emissions, which is in Africa and South America, which we expect near the tropics. And so what I do with this model is I add these emissions, and then I allow the model to do a 3-year-long simulation. And then I can calculate the resulting mixing ratio of my gases across the globe, and in particular over Greenland and Antarctica. Okay? And so I'm going to define a term called sensitivity, which is the parts per trillion, or the amount of ethane or acetylene I get over Greenland or Antarctica for a given mass emission of from a certain region. So PPT per teragram per year. And so in this case, for global fire emissions of ethane, we get about 41 parts per trillion per teragram per year of fire emissions. And then for Antarctica, we get about 29 PPT per teragram per year. Okay, so I'm going to use these sensitivities to try to infer different fire emission scenarios that can reconstruct our ice core levels. Okay, so I'm going to first talk about acetylene, because this gas only has the one source, right? The biomass burning source. And now I'm focusing just on the last 1,000 years. So our time scale here is just 1,000 to 2,000 CE. And the vertical axis in this panel is the emissions, or the fire emissions of acetylene in the units of teragrams per year. And I want to talk about 2 time periods from here on out, so let's just get acquainted with those. The first is the medieval period, which is from 1,000 to 1,500 CE, which is the red or pink, these projectors, color there. And then we have the little ice age, which is from 1,600 to 1,800 CE, denoted with the blue. I'm going to get rid of those for simplicity, but I'll talk about those a lot from here on out. So what I did is I used this simple grid search approach where with those sensitivities, I can scale or range biomass burning emissions from the global footprint and solve to find emission scenarios which can reconstruct the mean ice core level of acetylene during the medieval period and the little ice age. Okay, so on the left here is the global fire emissions of acetylene needed to produce those lines there on the right. So I'm showing you on the right the resulting mixing ratios from the scenario on the left, and the markers are the actual ice core levels. So with this scenario, forcing global fire to increase or decrease in sink, we see that we can do a really good job of reconstructing the Antarctic levels. The line goes right through the mean. But for Greenland, we can't do that. Okay, so we underestimate Greenland levels, especially during the Little Ice Age. But this scenario tells us that there had to be a very large change in at least the global fire during that time, about a 50% decline. And also this emission scenario makes us have about 4 times modern acetylene emissions during the medieval period. So that's forcing acetylene to go 4 times in the past. So that's a lot of change. So I wanted to explore different scenarios to try to do a better job of reconstructing the Greenland data. So what I did is I divided the global distribution of fires into 2 main regions. The non-boreal region, which are fires from 50 degrees north to 90 degrees south, and then the boreal region, which are fires north of 50 degrees north. I recalculated those chemistry transport model sensitivities, and then I did the same type of grid search. So now these 2 regions are allowed to vary independently through time. And so what you see, emissions on the left and the resulting mixing ratios on the right, it's a much better agreement. And what we see is that we don't really need any change in the boreal fire emissions of acetylene, but what we do need is about a 50% decline in the non-boreal region, which is mainly comprised of tropical fire emissions. And again, we see that we still need about 4 times modern burning during the medieval period to reconstruct the ice core levels. And for reference, I forgot to mention it on the last plot, that star on the far right on the left panel is the modern day acetylene fire emissions. So just about 1.2 teragrams. So significant changes to the acetylene budget in the past. So we can also do this for ethane. But ethane is now a 3-dimensional problem because on the x-axis here, I have non-boreal fire emissions of ethane. On the y-axis, I have boreal fire emissions of ethane. And then on the z-axis, which is going up in my little what I call pizza slices, we have the geologic emissions of ethane. And what I'm showing you are contours of goodness of fit. So the redder the color, the better the fit that emission scenario of non-boreal, boreal, and geologic emissions is to the ice core data during the medieval period. Okay, so I can do the same thing for the Little Ice Age. And you can, if you're really good at seeing these colors, you can see that they shift to the left a little bit. So this is hard to imagine. I'll get into a better scenario here in the next slide. But I also wanted to emphasize that with this ethane modeling, I had to make assumptions about what the chlorine sink term was. And in this case, I'm showing you when there's 60% of loss is due to chlorine atoms. And I'll get back to a case where there's 0% loss. Okay, so now if I just zoom in onto 2 cases, I'm showing you on the left the ethane emissions from the non-boreal region in black, the boreal region in blue, for a case when there's no geologic ethane emissions in the dashed lines, and then some geologic emissions in the solid lines. And then on the right panel, you have the resulting mixing ratios again, with the black line being the geologic case and the dashed red line being the no geologic case. They're identical because my model's forcing to find the solutions that fit the data perfectly. And so what we see on the left panel is that regardless of our assumptions about the geologic source, so the black dashed line or the solid black line, it requires that non-boreal emissions decline going from the medieval period to the Little Ice Age. Okay, so just like acetylene, we see a large decline in the non-boreal fire emissions. And also just like acetylene, we need a significant change to the global footprint or the amount of ethane emissions. So the yellow star on the left panel is the modern day global fire emissions of ethane, which is about 3.5 or so teragrams per year. And during the medieval period, we need about 2.5 times. So a big change again. Okay, so that's great. I have 2 records. I have ethane and acetylene, but just to make things more complicated, I guess that's what a PhD is about, I'm going to also include methane. So if you remember from the beginning, that proxy record I showed you from methane, that record was done or reconstructed by using ice core measurements of the mixing ratio of methane, as well as its stable isotopic composition. So that data is available on a model that solves for both the mixing ratio and its stable isotopic value of methane to find what emission scenarios of fire can I reconstruct? So the model includes sources from biomass and biofuel burning. Wetlands are the biogenic source of methane, and also this geologic source that ethane might also have. So because this is an isotope model, I have to include the isotopic end members of these of these emissions. And so you can think of the end member as kind of like the fingerprint of that source. So if I were to go out and measure some methane outside, bring it back to the lab, and I measure its C13 value at -60 per mil, then that gas sample I took was most likely biogenic in origin. Okay, and so the model solves for the balance of the isotopes and the amount of methane. The model also has some sinks, not going to get into it, but we can talk about that later if you want. So now I'm showing you again the same type of contour plot for methane. We have all biomass burning emissions on the x-axis, and then we have microbial emissions on the y-axis going into the screen, and then upwards in the up direction, we have the geologic emissions. Again, the redder the color, the better the fit to both the ice core mixing ratio of methane and its stable isotopic value. Now you'll notice here, for methane, we're not distinguishing between non-boreal and boreal emissions. And the reason we can't do that is because the methane lifetime is so long, you only get an integrated global perspective of fire, okay? Again, just like ethane, I had to make some assumptions about the chlorine term, so I assumed 5%, which is kind of the maximum amount that is thought to be. Okay, so on the left panel here, I'm showing you the budget of methane. So in black is the biomass burning term, and in red is the microbial term. And then in the right panel is the resulting C13 of the methane from that emission scenario. Again, in the dashed lines, we have no geologic emissions. And then in the solid lines, we have some geologic emissions. Okay, so what you'll notice is that just like ethane and acetylene, we have a large decline in the biomass burning component of methane, and the microbial component increases, but I'm not interested in microbial stuff anyway. Okay, so also the reason we have these big changes in the budget is because the isotopic value of methane changed quite a bit during that time. It changed by about 2 per mil. So a significant change in the sources of methane. Okay, so now I have the 3 different records, methane here in black, ethane in green, and acetylene in blue. And these are the fire emissions of those compounds for the last 1,000 years for this scenario here. So this scenario I'm showing you is when we have no geologic ethane or methane and no chlorine loss for methane and ethane, because I wanted to explore the full range of geologics in the chlorine term. Okay, so there'll be more panels coming. Also on the right here, those dots are the modern estimate of fire emissions of these gases. So we want to see differences between these records because we know that we get more fire emissions of methane than ethane and acetylene, right? Because these are the emissions of each gas separately in the units of teragrams ethane per year, teragrams acetylene per year, et cetera. So if I show you the remaining scenarios, we now have a case where there's no geologic ethane or methane, but high chlorine sink for ethane and methane. Then the low geologic case, no chlorine, and low geologic case, high chlorine. And so you'll see that the methane line, the black line, and the ethane line, the green line, move up and down. The acetylene line doesn't change because we didn't have any of those complications of geologics and chlorine for the acetylene budget. And so we see these moving up and down, that's great. But how do I determine if there was a single fire history from these records? This is not telling me what I need to know because right now I'm comparing apples to oranges. I'm comparing the emissions of methane to the emissions of acetylene, but that doesn't make sense because we know they're already going to come out of fires at different ratios. So what I'm going to do is I'm going to apply an emission factor. So emission factors are the grams of your compound, say acetylene, released per kilogram of dry matter burned. So dry matter burned is the material or the mass of stuff that's burning. So these emission factors are relatively well known. They're measured in the field and in laboratories. And so I can apply some best estimates of these ratios to those records on the left, which are still in the units of teragram species per year, multiply them by those emission factors, and now these are all in the unit of dry matter burned per year, with acetylene in blue again, methane in black, and ethane in green. So what you'll notice is that the methane and ethane record converge to a very similar dry matter burned history, which is important because there's only one atmosphere, there's only one Earth. So if these are recording fire emissions or dry matter burned emissions, we should be seeing the same history. And what you'll notice about acetylene is that it's about 50% higher during the medieval period compared to the other two records. Okay, but this is just the no geologic, no chlorine case. I still have 3 other cases to explore. And for reference, today's modern dry matter burned estimate is the star in the right panel, which is just a little under 5 petagrams carbon per year. Okay, so now I have 4 different scenarios, and what we want to see is that all of these lines converge to the same history. And you'll notice it doesn't happen, which I guess is the joy of a PhD project. Okay, so we do see that for the most part, in each panel, 2 of the gases converge to the same history. In the second panel, you see that the blue acetylene line and the green ethane line converge, but methane is falling short. And then in the third, you see methane and ethane agreeing again. And then in the fourth, everything's kind of spread apart. So we don't get a single fire history from this approach here. But what I do want to point out is that all the dry matter burned histories indicate a large decline in dry matter burn from the medieval period to the Little Ice Age. So they're consistently getting that finding. And also, for most of these records, the medieval period dry matter burned rates are comparable to modern day or greater than modern day by significant change, especially for acetylene. So during the medieval period, say in the first panel here, acetylene dry matter burned is about 15 petagrams per year, and today it's only about 5. So you see a 3 times change. So acetylene is forcing there to be a significant change in fire in the past. And again, no scenario provides a consistent history of fire. So some hypotheses that could explain those differences. One could be lifetime, because these are shorter lived gases, etc., but that's not likely because there's a lot of research into the change in the oxidative capacity of the atmosphere in the last 1,000 years, and it's pretty inconclusive that there's any change. Transport changes. The climate of the last 1,000 years was not significantly different than today, right? It's a few degrees, etc., but not significant changes in the global atmospheric transport. So probably not transport. The third hypothesis is biofuels. So I mentioned in the beginning, we thought that biofuel term would be low. And for all of the modeling work, I assumed those values were constant through time and at a low level. But biofuels may have actually changed a lot in the last 1,000 years. And this paper came out earlier this year, and it was talking about the location of, civilization and indigenous populations in the Americas and how those populations declined, especially after European contact. And we know that those populations used fire in their lifestyles. And so if the location of biofuels and its magnitude changed through time, we weren't capturing that in our approach. So future work should look at the change in biofuels through time. Also, I'm assuming that those emission factors I applied were constant through time. And that assumes that the biomes or the material that's burning also didn't change, that it's identical to today's footprint. So maybe not the best approach, but we'll work on it. Okay, then we also have this potential acetylene source from geologic emissions that I mentioned in the beginning. So if acetylene were to have more emissions from, say, a geologic source, it wouldn't need as much biomass burning to reconstruct the ice core levels. So maybe that could bring down the differences we see in the dry matter burn histories. And finally, methane is complicated. Okay, so in order to reconstruct the fire component of methane, we need to make assumptions about this C13 value. And we know that the C13 shifts through time based on the amount of C3 or C4 plants. And so we also know that those ratios change through time. And so you need a dynamic C13 value for all of the methane sources, and those aren't easily to come by. So methane complicated. So to conclude, I'm doing good on time. Okay, we have new ice core records of ethane and acetylene. These are the first ever records of these gases ever. So I'm really excited about that. Ethane, acetylene, and methane all show a large decline in the biomass burning source going from the medieval period to the Little Ice Age. And the ethane and acetylene fire histories are more consistent with the methane fire history than the record from carbon monoxide and charcoal, which makes you think that we should not be using those gases and those records for fire models. But again, no scenario that I explored provides a consistent history of fire, but that doesn't mean it doesn't exist. I think a lot of the discrepancies or differences we're seeing has to do with some of those hypotheses I was mentioning. And again, methane is complicated, especially over very, very long time periods, say coming out of the last glacial maximum when the whole landscape and transport was different. We don't know those C13 values. And so it's probably better to use these gases like ethane and acetylene, which don't need that C13 value, to better understand fire emissions during those time periods. So future work, more work is needed to reconcile these gas records. So that's what I'm doing this summer, I think. And then I'm also going to extend the ice core records of ethane and acetylene back to the last 50,000 years or so, during the last glacial maximum and termination, to really get a better sense of the variability in fire emissions, and maybe the climatic controls on those emissions. All right, so quickly to acknowledge, so it takes a village to finish a PhD, and I just want to acknowledge my advisor, Eric Saltzman, who many of you may know was gone for 3 years during my PhD. But I have to give him credit where it's due. He was still a phenomenal advisor. He was still a phenomenal advisor nonetheless, and I'm really thankful for all your input and guidance. You only drove me nuts a few times. Okay. My co-advisor and Antarctic travel companion, Murat. Murat's a good guy, and he has a lot of patience. It seems that every time he left the lab, something broke, and so he always blamed it on me. But he did show me how to gut a mass spectrometer and put it back together. So thank you for your input and guidance over these last 6 years. My committee members, Ellen, Don, and Michael, thank you for all of your insightful committee meetings. It was really, really helpful. Also, my lab mates, so my lab changed a lot. So we have John and Kaden now, but there used to be a bunch of us. Thank you all for everything. If you're watching, I'm YouTube living right now. Okay. And then the ESS community at large, this is the best department ever. I'm just gonna say that. Everyone is so inviting and welcoming, and I've had so many great memories with you guys, and I'm gonna miss you guys. Okay, not crying. Okay. Also, Julie is about 5 foot 2 inches tall in that picture. We went to Tanaka Farms. Okay, I also want to highlight our anomalous spikes volleyball team. So you guys have been a really great outlet for energy and aggression during this last few years. Also, I want to point out that Dylan is our Anthropocene here. And then we have Jessica, our little ice age, and Kevin, our medieval climate period. And then I guess I'm like the little last glacial maximum or something. Okay. We don't usually win our games, unfortunately, but it's still fun. I'd also like to thank my far, far away friends who actually came today, Ashley, her husband Marcel, and their daughter Madeline, who's been impressively well behaved during this whole presentation. I really appreciate you guys coming. You've been a great support system over the last 6 years. Also, last but not least, my family. So my family spread out all over the country, so it makes it hard to visit them. My dad, who's in Pennsylvania, my grandparents, who are also in Pennsylvania, and then my mom's here today. She's a great woman. So if you think I'm great, please talk to her at some point today. She's phenomenal. Also, my boyfriend, Matt, who decided to start dating me during this last year of my PhD, which speaks a lot to him. So thank you for everything. And his family, Ellen and Jay, for giving me dinner every single night. I really enjoy our time together. It's been great. And if I'm missing anybody, I'm sorry. And thank you. So this is me taking a nap at the South Pole.
Okay, questions from the audience?
Yes, Sergey.
Yeah, this is very nice. So if you had CO and CO2 measurements in parallel, in principle, you could calculate modified combustion efficiencies from those two, and from those calculate how emission factors changed over the time, and potentially account for some of the uncertainties that you don't know what was going on with emission factors over the time.
Yeah, that's a really great point. However, CO measurements and ice cores are really hard to make. But I think there's groups up in New York that are attempting to do that. But yeah, no, I agree. Having more records of these different trace gases would really help constrain those emission factors. Julie?
So I understand that the geologic sources are not so certain, but I'm really surprised that chlorine causes that level of uncertainty. Can you explain a little bit why we don't know more about what's happening with chlorine?
Yeah, so chlorine is a hard gas to model. So actually just last month, a paper was published that used the geochem model to do a global perspective of the chlorine budget. So it depends a lot on how clean the air is and what the sources are. And for ethane in particular, ethane is really reactive to chlorine compared to methane. And so even just changing the knob on that a little bit, you really change the budget a lot. So there's been very limited work in that field. So hopefully people can get a better sense of that ratio between methane and ethane, because a lot of our uncertainty is, in that spread in the chlorine term. But I can't really answer the question because I don't know much about chlorine.
You separated boreal from non-boreal. Could you do some additional level, like boreal, temperate, and non-boreal?
Yes, good question. You can, but then it makes it very hard to interpret. So when I start doing those 3-dimensional panels, for every source you add, you'd have even more panels, So yes, you can. At some level, the sensitivities need to be different enough for it to matter, right? So the boreal sensitivity for Greenland ethane is really high compared to non-boreal. So that's really the knob that's pushing those up and down. So if the sensitivities are all the same, it's not going to know which source to push up and down, kind of.
So yeah, really great talk. I have one comment and then a question. My comment is that for the contemporary biosphere and fires, I think we're still low by as much as 50%. So when you're trying to pin it to the modern, I think it's really hard to see these small fires. And there's a paper that's coming out this year, I think in Nature Geoscience, that says for Africa, we've underestimated burned area by like a quarter or half. So,
right.
So when they're using high resolution data. So that might help pull it up a little bit. So don't take that too seriously.
Yeah.
The question is, what about to try to bring reconciling the methane and the acetylene together, if you pushed the emissions a little bit further south, or the drop off further south to like South Africa or Southern South America, could that help you?
Very good point. So I did look at what happens if you allow South America acetylene. So acetylene over Antarctica is very sensitive to South America emissions. It's the highest sensitivity in that region. And so yes, you can reduce the total amount of biomass burning needed, but then you start pushing it into, is this a feasible number? Like it would need to completely shut down in South America during the Little Ice Age if you're forcing the decline only in that area. And also I think, if I remember the numbers, I needed like 6 to 7 times more fire in South America during the medieval period. So a very, very significant change. Claudia?
Yeah, can you talk about the increase in the microbial sources of methane during the Little Ice Age?
Yeah, I mean, I can try. I don't. So it's a lot to do with the location of wetlands, with the temperature change. I personally haven't focused a lot on the microbial. So the microbial C13 value is very, very low compared to biomass burning. And so I think with this approach of forcing burning and microbial to change, it really wants to pull microbial up, really to create that decline in the C13. But I myself am not very certain on what scientists think the microbial increases from. Yeah.
So there's a lot of great measurements here. So good work there. So I was really interested in the differences between Greenland and Antarctica. And from what I understand, the ice isn't necessarily the same between the regions, right? Greenland is dirtier and there's potentially
yes. So it's a really great point. So that Greenland record, that ice core was drilled in 1989, which is older than me. And so that ice was also stored in freezers with high levels of CFCs and all that kind of stuff. And it is older ice. So the quality is not as great as, like, say, the South Pole ice core, which was freshly drilled a few years ago, and it was drilled with a better drill, et cetera. So yeah, one of the things that I haven't really looked into would be like the ice chemistry. So if there's particles in the ice or the water itself, when it's melting, could that be producing these gases? It's really hard to say. This is the filtered data. I've pulled out measurements that are really awful from like experimental issues or things like that where I think I hit a dust layer or something. But yeah, I mean, for the Antarctic record, it's remarkable how well from waste divide, so the red and the blue are from the waste divide ice core from West Antarctica, and the green is the South Pole core. They have different levels of accumulation, different transport and moisture sources, and you get almost the same record. They're off by like 1 ppt, which, you know, analytical uncertainty. John?
When your high chlorine sink for ethane, how high was that relative to OH?
How high was it relative to OH? So the way I did it is I scaled the value. So it was 60% of the total loss. So then 40% was from OH. Yeah. Any other questions? A lowball question? Just kidding.
So many changes to the OH sink?
I did not assume any changes to the OH sink. And that's really because there's this recent ACC-MIP compilation that tried to explore the changes in OH from the pre-industrial to modern, and mainly for methane, but you know, OH with methane is the same for these gases too. And that change was to plus or minus 10% or something. So they didn't really get any change. I mean, you could change the lifetime, but then it's another knob. So it's a really complex story. But yeah, lifetime could potentially be happening.
I have an easy question.
Okay.
What falls under the umbrella of geologic?
Yeah, geologic, so that's just natural like seepages, mud volcanoes, thermal vents, stuff like that.
So the ocean?
So the ocean sometimes, but mostly near like the continental shelf, because a lot of this stuff would get eaten up by critters throughout the column of water. This geologic source is just, I don't know, I'm confused about it a lot. I've been emailing the guy who has proposed this geologic source, and because it is proprietary information, because, you know, oil and gas, he doesn't necessarily want to send me a lot of information about it.
Okay, well, let's thank Mindy again. Thank you all for coming.
Thank you.
It wasn't clear whether you were excusing him for being gone for 3 years or excusing him for the 3 years that he was here.
Thanking me for being gone.
You were at the wedding.